Hello world, welcome to yet another episode of Netmother Tech Academy. Today we are going to look at Python programming and the use case that we have taken is Fibonacci series. We are going to do Fibonacci series in three different ways. One is recursive, the other one is recursive with memoization, and then finally Fibonacci series in dynamic programming, and see the difference in performance between these three options. Let's get started. So the first method we are going to try is by recursive method. So for our series, we know it starts at 1, 0, 1, then it's always the sum of the previous two numbers. So it goes like this. So we want to write a function to do this. So let's call it recursive and let's pass the number to it. So if the number is 0, then we know we have to return 0. Or if the number is 1, then also we have to return 1. Those are our base case. Otherwise, what we do is we simply return the Fibonacci recursive of the previous two numbers after summing them. So num minus 1 and num minus 2, the previous two numbers. So that's pretty much it. Let's quickly check if it's working. So let's call the Fibonacci series the fifth element. We have to print it to verify it. So we get the answer 5. So 6, we should get answer 8. Okay, that looks good. Now that was pretty simple, but let's see how this algorithm performs. So to do that, I'm going to import time, and I'm going to have a variable called start, and I'm going to record the time. And let's calculate the end time after calling the function. And let's print the total time taken. So that'll be the time taken for recursive. So let's see how this goes. So please note that there is e to the power of -5 here. So it wasn't so bad, but you will see as this number goes higher and higher, the time taken will also grow exponentially. So for a number of 15, we get 0.00037 seconds. So if I go 20, not so bad still, but let me try 30, and we get about 0.5 seconds for it. Now, what is the problem with this approach? Problem with this approach is we repeat calculations. For example, if I'm doing Fibonacci of 5, at that point it's gonna call Fibonacci of 4 plus Fibonacci of 3, and which in turn for Fibonacci 4 is gonna call Fibonacci 3 function again, and then the same calculation will get repeated again and again. We want to try and avoid it. So let's go to the second algorithm. This is also Fibonacci recursive, but with memoization. So for this, we are gonna try and remember all the previous calculations that we have done, so we don't have to do it again. So the algorithm is gonna be the same. Now while you can notice that the time taken was almost a minute for the number 40. So now let's see how to do this one. So I have copied the same algorithm, but I'm gonna capture it in a variable answer, and I'm going to add this answer into my memorization list. So it could either be a list or a dictionary. Let's go with the dictionary approach. So I'm gonna check. I'm gonna say memo of num is equal to answer. So I'm basically storing the answer. And while the function is called, we should also check if the num is in memo, then we will not repeat the calculation again. We will simply return memo of num. Now, at every point where we are doing a return, we also have to make sure we are returning the memorization dictionary. We want to keep track of all the previous numbers. So next time when we call, we need to pass the same history or log of all the calculations. So we are gonna add into our return statement the actual memory of the previous calculations as well. So that means we need to break this statement. So let's calculate answer 1 and answer 2. And in here we have to do answer 1 plus answer 2. And for while calling this function, we have to pass our memory. And finally, we can return memo of num, comma, memo. So let's first check if everything is working fine. So let's call this function, and we do not need this one if we already create a dictionary and we say the answer for 0 is 0, the answer for 1 is 1. So now I call the function, let's say for 4, and pass the memo, and let's print our answers and see what we get. Let's stop this and comment out this line. We already know for 40 it took about a minute. So we get the answer 3, and we also can see the growing list of memoization here. So for 0, the answer is 0, 1 is 1, 2 is 1, and 3 is 2, and 4 is 3. So this order. Now let's try and increase this number and make sure everything works. Perfect, that was faster. So we get 5, 8, 13, 21, and there goes our list. If you remember, for the number 40, let's make a variable for the test num that we have when we are going with 40. So let's use the same test num here, and let's see how many seconds it takes. So we need this one here, and this is the time taken for recursive with memory of previous calculation. So let's run this, and we see the time taken is very less when compared to the other one. Here it takes about 5.8 to the power of minus 5, 10 to the power of minus 5 seconds, which is very less when compared to almost a minute when it took for this simple recursive problem. Now let's try and up this number and go to 60. Still, it's much better. When we slowly increase the number, we see a rise in the time that it takes. And for 500, the time taken is still 0.01 seconds, still negligible. I have exceeded the maximum recursion if we go for such a high number. Let's try 1000. Okay, still. So Python has a limitation of the maximum recursion that we can do. So let's stick with 600, let's say. And the time taken is 0.02. So instead of printing everything, let's print only the answer. The answer we got is a big number, and the time taken is 0.0006. Now, how can we improve this even further? Like for the case of 1000, this algorithm failed. And that's when we can do dynamic programming. So in this technique, what we are going to do is we are going to have one single loop with a list. We are going to dynamically calculate the values by adding the previous two elements in the list. For example, I have a fib list here, and I know the first element in the list is 1, second is 1, and now all I need to do is to calculate the third one. I have to sum up the previous two numbers. So let's make a function for it. So this is going to be Fibonacci series dynamic. When we actually want the number, and then we want uh, the list. So all that we are gonna do is run a loop. So for I in range num, and we already know for 0 and 1 the indexes, we know the answers. So we can directly start running the range from 2. So all we have to do is inside the fib list, we have to append. So fib list dot append the values of the previous two numbers in the list. So it's going to be fib list of I minus 1 plus fib list of I minus 2. And finally, after the loop is run, so this algorithm will be order of n, just one single loop. All we have to do is return fib underscore list of num. So now let's see if this works. So I'm gonna print and call fib dynamic and pass the value 30. Let's change this to 30, and let's use the same number, same variable here, 30. And let's see if we get the correct answer. So we need to pass the fib list here. So we get the same answer, and if you see the time, not much different. Both have performed really well. Now let's comment out the memoization call and try to do a higher number. And we see it still works. And the time it took was still 2.3 to the power of -7, which is still a very, very good time. Let's go ahead and try for 500 and let's do both the algorithms. And it's good. Let's make sure we get the same answer. Yes. And time taken for, oh, we never printed the time for this one. So sorry. So we need to copy this code, paste it here, bring this one in here and change this to dynamic. So now if I run it, the time taken for recursive with memory was 0.0005, whereas this one is almost 5 times faster. And we didn't even call the first algorithm. That would not even be possible. Even for a value of 40, this took about a minute. Okay, so hopefully you guys learned a little bit from this exercise. Again, whenever dynamic programming is possible, this will save us time, memory, and also perform much faster. Memoization is not a bad idea. In a recursive call, we have to be aware of the maximum recursion that we would reach. So for higher numbers, this might not work out, but it definitely speeds up the process and avoids duplicate uh, problem solving. And the first approach is only probably good till a really small range and is also not the efficient because it repeats the same computation again and again. Wonderful. Thanks everyone for joining and tuning in. We'll meet again in the next video. Bye world.